Welcome to Lesson 11b, Oblique Shock Equations. In this lesson, we'll derive the conservation equations across an oblique shock, and then we'll compare these equations with those of a normal shock. Now let's start to look at oblique shocks quantitatively. Here's our oblique shock, with 1 before the shock and 2 after. We'll let v1 be the velocity approaching the shock. The shock itself is inclined at shock angle beta, and the flow turns at some smaller angle, the turning angle, theta. Let's split this velocity v1 into two components, v1t, which is tangent to the shock, and v1n, which is normal to the shock. We'll do the same with v2. v2n will be smaller than v1n across the shock, and v2t will be the same as v1t. v2 is the vector sum of these two components. Doing a little bit of trig, this angle is beta minus theta, this angle is beta. So we can write v1n equal v1 sine beta, v1 tangential v1t is v1 cosine beta, v2n is v2 sine beta minus theta, and v2t is v2 times cosine beta minus theta. But as I said, the tangential velocity components are not affected by the shock, so v1t equal v2t. This is the key to our quantitative analysis. Namely, the tangential component of the oblique shock is not affected by the shock. The flow tangential to the shock is the same on both sides. Thus, our old normal shock equations still apply, but in terms of the normal component of velocity. Not v1, but v1n. This allows us to calculate all the property changes across the oblique shock. I'll illustrate with a small control volume. Here's our oblique shock from 1 to 2, and here's a slice of a control volume across the shock. v1n is the normal component coming into the control volume, and v2n is the normal component coming out. But v1t and v2t are the same, and they move parallel to the shock into the control volume and don't change. Therefore, the same flow comes out the control volume. Let's define this face area as A. Now we can write our conservation equations. Conservation of mass on this control volume gives us ρ1 v1na through the normal component at the inlet equal ρ2 v2na at the outlet in the normal direction. In the tangential direction, the same flow comes in as comes out, and since the area is the same, we have ρ1 v1n equal ρ2 v2n, which I'll call equation 1. For the momentum equation, nothing changes at all in the tangential direction, so we need to consider only the normal direction. We have P1a acting in this direction, and an opposing P2 acting in that direction, opposite, and we expect P2 to be larger. So our momentum equation is P1a minus P2a equals sum over all the outlets of m dot vn, the normal direction, minus the sum over all the inlets of m dot vn. So this is the momentum equation in the normal direction only, while m dot is ρ2 v2n times a, as we saw up here, and vn is v2n at the outlet. At the inlet, m dot is ρ1 v1na from here, and Vn is V1n. The pressure force is P1a minus P2a, and there's an area in each term which cancels. So our momentum equation reduces to P1 minus P2 equal ρ2 V2n squared minus ρ1 V1n squared. We'll call that equation 2. Conservation of energy tells us that stagnation enthalpy must remain constant. So specific stagnation enthalpy H01 equals specific stagnation enthalpy H02. For an ideal gas, this reduces to stagnation temperatures being equal as well. Well, recall that H0 is h plus 1/2 v squared, but this v squared is the total velocity magnitude squared. And scrolling up, we see that v1 squared is v1t squared plus v1n squared. Similarly, v2 squared is v2n squared plus v2t squared, since these are right triangles. So our enthalpy equation can be written out as H01 equal H1 plus 1/2 V1n squared plus 1/2 V1t squared equal h2 plus 1/2 v2n squared plus 1/2 v2t squared, which is equal to h naught 2. But v1t equal v2t, so these two terms cancel, and thus our energy equation reduces to h1 plus 1/2 v1n squared equal h2 plus 1/2 v2n squared, and I'll call that equation 3. Now I want to compare the normal shock equations and the oblique shock equations. These are the mass, momentum, and energy equations for a normal shock that we've been using for many weeks now. And these are the three equations that we just derived for the oblique shock. You can see that these equations are identical if we replace v1 by v1n in all three of these equations, and v2 by v2n. Let me look at different frames of references to try to make this more clear. In the typical stationary frame of reference, we have the oblique shock, v1, with turning angle theta and shock angle beta, 1 before the shock and 2 after the shock. Now let's rotate this whole thing by 90 degrees minus beta, which will make, in our rotated frame of reference, the shock be vertical. So v1 comes in at this angle, v2 at this angle. We still have 1 and 2 across the shock, and I split the velocities into the two components on each side. This angle is beta minus theta, and the shock angle is here, beta. Now we take this rotated frame of reference, and we move up at speed v1t, or v2t since they're the same. Now what do we see? Now it looks like a typical normal shock from 1 to 2, with some flow coming in and some flow coming out. So imagine that you're a camera moving up at this tangential speed v1t. This is what you would see. You would see exactly a typical normal shock. You wouldn't see any tangential speed since you're moving at that same speed. So it's no wonder that these equations are identical if we replace these speeds with the normal components. Let's write some equations for m1n and m2n. m1n, the normal component of Mach number, is v1n over a1, which is v1 sine beta over a1, but this is m1. So m1n is m1 sine beta. I'll call that equation 4. m2n is similar, v2n over a2, or v2 sine beta minus theta over a2. So m2n is m2 sine beta minus theta. So the bottom line is that we can use the same normal shock equations that we used before, except with m1n instead of m1, and m2n instead of m2. For example, we had an expression for P2 over P1 as a function of m1 and gamma for a normal shock. Well, for an oblique shock, we can use the identical equation, except use m1n instead of m1. I'll close with this comment. Since we've transformed into a normal shock by rotating and moving, we must have m1n greater than 1, and we must have m2n less than 1. A shock still must go from supersonic to subsonic, even if it's oblique. But for an oblique shock, the actual m2 can be less than, equal to, or greater than 1.
I thought the flow downstream of a shock always had to be subsonic. How can it be supersonic downstream of this oblique shock?
Well, Jack, Mach number is based on the total magnitude of velocity, not just the normal component. If the tangential component is large enough, the Mach number m2 can be greater than 1.
Oh, that makes sense. Thank you, sir.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.